First of all, I'd like to say a warm welcome to all of you from sunny Brisbane. As we are coming close to the end of the year, and what a year it has been, saying that I wish that all of you and your loved ones are safe, sound and healthy in these turbulent times. Before starting, I'd like to quickly note that the audio and video for the participants will be off, but you'll be able to ask questions on the right-hand side of the screen, which will then be responded at the end of the event. We are also recording the webinar and we'll share the recording with you after the event. Saying that, of course, no personal information will be visible on the recording. On the event board, on the top right-hand side of the screen, you can find the slide decks as well on the files. So you can download them from there. It's a great privilege for me to host this webinar, which will be presented by Power Quality Solutions guru, Dr. Alper Terciyanli, who worked as a chief researcher in National Research Institute of Turkey many years, and then set off to found his own company, Endoks, with two distinctive fellow researchers, which then also became one of the few companies in the world providing power quality solutions in medium voltage. He's got patents for power quality solutions and is still leading Endoks as CEO. It's my absolute pleasure to give Dr. Alper to you today. Over to you, Dr. Terciyanli.
Thank you. Thank you so much, Serdar. And hi, everyone. It's really good to have such a meeting with you, all you actually. And today I would like to tell about a little on the power quality and what's power quality, how we can improve that. And let's first start on a couple of slides, actually, who we are and what we are doing. We are established a company after more than 10 years experience in a research institute, governmental organization, and established a company. And now we have operations in many countries, including India, Australia, US, and Turkey, and many countries we are selling. And the now team is more than 50 people, and then most of them are electrical engineers. And this is our journey. As I told, actually, we established the company in 2008, and now we are working mostly on the power quality, IoT, and the SCADA and automation products. This is our team. I am one of the co-founders. We established the company with my colleagues Alper and Adnan, and then our Indian partners, our friends, joined us, the Barani and the Mr. Pandian. And since we had been working with an R&D institute, actually, and Endoks' main motivation is the R&D projects, because we are in these R&D projects, we are developing new solutions or new hardware, and also all the products right now we are offering to the market are outcomes of these R&D projects. Our solutions we can this actually classify in three main titles. One is the power quality, of course the main locomotive of the company, and the automation, the industrial automation solutions, and also IoT devices, which we are manufacturing our IoT devices for monitoring and control applications. But today we will talk about power quality. And first of all, I would like to start with the definition of power quality. What is power quality? Actually, it is any problem manifested in voltage, current, or frequency deviations that result in failure or misoperation of end users' laws and equipment connected to power system. Actually, we can tell that we have an ideal case, which is the supply should be pure sinusoidal waveform with the definite frequency, the period, and also definite waveform. And on the other side, on the load side, the current should be ideal. So if there's any case which we are apart from these ideal cases, then we can talk about power quality. So why do we need to improve the power quality? Because the power quality causes failure and the damage of equipment. It causes additional losses, malfunctioning of protection devices, or process interruption or slowdown, or the penalties because of low power quality. Of course, in many countries, actually, in many countries or all countries, there are some regulations on improving the power quality. So we are following these regulations or the guidelines, technical guidelines, to improve our power quality and avoid any problem raised by the poor power quality. And according to IEEE, the 1159, and also there are some in IEEE 519, we have some parameters defining the power quality. First one is the transients. Transients are the impulsive or oscillatory waveforms during, for example, capacitor switching, reactor switching, or there is a strike, lighting strike on the power system, or switching of the long but unloaded overhead lines. All these impulsive and oscillatory variations on the system, we call it transients. And also there's another definition for these interruption or these variations are the short duration variations, mean the interruption and sag and swells. Actually, interruption is, we know that there is no supply. For the sag and swell, which is I think the most common power quality problems we observe on many systems, the sags and swells. Sags and swells actually occur because of again the sudden switching of some loads like capacitor switching, or heavy big loads like motors or transformers, energizing transformers. And these sag swells actually seen on the system starting from the milliseconds up to 3 seconds. So if there is a change in the magnitude of the voltage, I mean the low voltage or the over voltage, then we call it sag and swell. And the bad things about the sag swell is, it's very short duration, and also it affects many equipment. On the other hand, it is very difficult to get some measures to avoid the sags and swells, because it's very short term. So the solution should be also responsive such kind of short duration variations. And the long duration, the under voltage and the over voltage. The under voltage and over voltage, I mean that it is, for example, 10 minutes average value of the voltage. If we say it is under the definitions, for example, EN 50,160, we call it 0.9 per unit up to 1.1 per unit. So there is a band there, the hysteresis band. So if the voltage magnitude is out of this band, then we call it over voltage or under voltage. The voltage imbalance is also another problem, and mainly on the low voltage side, we observe the voltage imbalance, and on the medium voltage side, we see these imbalances mostly on some special industrial loads like the arc furnaces and the single phase loads like the railway applications, and we see the voltage imbalance. It is very important to avoid the imbalance, because in low voltage network, this imbalances creates neutral conductor currents, and this neutral conductor currents also can generate or can lead to the voltage difference between the neutral and the earth, potential earth. So this might affect some devices like the monitoring devices in hospitals or IT equipment. So this voltage imbalance, especially on the low voltage network, should be avoided. And on the medium voltage side, of course, it can create some triplet harmonics. So this imbalance, and then this triplet harmonics can cause some resonance issues on the medium voltage network. And the waveform distortion, we have the harmonics are the common waveform distortion parameters. The notes also another one. Notes are mostly because of some the power electronics devices like the motor drives, or some switching some loads. On the other side, harmonics again can be generated by the power supplies, converters, and the inverters, the motor drives, even the some lightings. The harmonics are the main one of the main parameters on our power system, which reduces the power quality and also creates some, the additional effects on the system, because any harmonics created by any load on the power system will create another effect on the voltage side, and this voltage harmonics also can create some additional losses or the currents on some loads like the capacitor banks. So and the other thing is the frequency variations, and that in Australia, of course, very well, in some countries, especially because of the imbalance in the demand and the generation, and also the variation of the generation, actually the resource, I mean, if it comes from the mostly wind and the solar and other renewable and the varying resources, then the frequency variation becomes very important. And in order to support these frequency variations, of course, there are some market operations, the FACs, and the frequency ancillary services. On the other side, the primary frequency control. But the frequency is also important because most of the equipment, especially the motors and the generators, are designed to operate at a certain frequency. And these are the parameters. I would like to mention one important thing here. Actually, the reactive power itself is not considered as an power quality parameter on standards. The voltage variation is a direct effect of the reactive power flow is a parameter. So personally, I prefer to classify the reactive power flow as also one of the power quality parameters in addition to these on this slide. And what are the effects of poor power quality? There are, of course, two stakeholders here. One is the grid operators, the other one is the end users. And for the grid operators, these power quality problems causing overheating on the cables or transformers because of harmonics, because of reactive power flow, failure of capacitor banks, mostly because of harmonics, and the trip of protection devices, the actual malfunctioning of the protection devices, again, because of the nodes or harmonics. All these protection devices may cannot measure voltage as they should, and because of nodes and the harmonics, and these mismeasuring causes malfunctioning of the protection devices. And of course, the harmonics creating an overstressing on the insulation equipment, and also over voltage. Over voltage is very, very important since the distributed energy resources are becoming more and more in the distribution system. Then the over voltage problems are becoming more important and critical for the grid operators. Because of these over voltage, there are many problems on the insulation equipment. And of course, the increased losses and the resonance problems are very important because of harmonics. Because in order to avoid the reactive power flow, you need to put reactive power compensation systems. On the other hand, these harmonics can create resonance problems on these cap banks. And of course, the poor power quality actually results in the poor supply voltage quality. There's a standard, EN 50160, which defines the quality of supply in terms of course, voltage. I mean the voltage magnitude and the imbalance and the harmonics, and also the flicker values. On the other hand, for the end users, this low power quality or the poor power quality causes process interruptions, additional losses, failure of IT or the monitoring devices in hospitals or in ITs, and also for residential, the customers, the failure of household appliances. But for industrial customers, it is very, very important to avoid these power quality problems. And I would like to give you some numbers. For example, I put here 3 cases. You see the marks there, where I get this information. For example, in Europe, in 2002, an actual survey from the Leonardo Power Quality Initiative, that there's a continuous operation in a facility, this power quality becomes very, very important. Textile, paper, and of course, semiconductor industries, and all critical industries having continuous operation. Any malfunctioning of the motor drive, any motor, or tripping of any motor drive in this process, continuous process, may cause the interruptions. And the bad thing is that all the raw material become an actually scrap. So the industrial facilities lose money and they lose time if there's a failure because of power quality. On the other hand, for example, in a bank, a fire resulting from neutral overheating causes over €1 million damage. Actually, as I told, and for the low voltage networks, for the low voltage networks, actually the neutral current is very important because of the unbalance issues. Because if there's an unbalance, and also if there's triplet harmonics on the lines, all these triplet harmonics and the unbalance current causes an current on the neutral conductor itself, and this neutral conductor current causes additional losses, heating, and also the potential difference between the neutral conductor and the earth potential. So this voltage difference also affects some sensitive critical devices like the ultrasound, the monitoring devices in hospitals or in other critical industries. So what would be the solutions for these problems? Of course, there are many solutions for each type of power quality problems, like the SVCs, magnetic control reactors, STATCOMs, static synchronous compensators, active and the passive harmonic filters, and these are all solutions for these power quality problems. But for the power quality, especially on the medium voltage network, all these power quality problems are a bit, each one is very special, and you have to find a solution for each specific problem. So the solution is a tailor-made solution at the end of the day, because the network parameter, the load parameters, all these parameters affecting the solution, and you have to design your solution based on this information. So that's why on medium voltage power quality, especially for medium voltage, the power quality solution at the end of the day is a tailor-made solution. And the application areas of these power quality solutions on industry, and what will be the benefits on the industry here. The elimination of current and the voltage harmonics, avoiding reactive energy penalties, and smoothing voltage variations are the benefits of the power quality solutions on industry. But the main benefit, of course, is the avoiding any interruption or the production itself, and also reducing losses and of course reducing the costs. On utilities, the voltage regulation on the lines and the cables is very important, which will increase the system efficiency with less reactive power and the harmonics, and of course combined with the regulations like EN 50160. On the other hand, the renewables part, for the application areas we are talking about on the renewables, the combined with grid codes for continuous and efficient operation, and also smoothing voltage to increase the production is important. In many renewable power plants, especially in our country nowadays, for solar power plants, because of over voltage problems, some of the solar power plants cannot operate during the days. For example, a couple of hours they cannot operate because the voltage rises up to 37 kV. It is supposed to be 33 kV, and so there's an increase higher than 10% on the medium voltage. So the inverters on the low voltage sides are tripping because of over voltage, and they cannot generate or they cannot produce power. On the other hand, the grid operator is also limiting the operation of these power plants, because the increase on the medium voltage level, the voltage of 37 kV medium voltage, means that on the low voltage side, for the low voltage customers, the voltage is also rising, and the grid operators are also avoiding these power plants to generate more power during the days and increasing the voltage. So for renewables, also the power quality solutions are very important. And what are the problems and the solutions I would like to tell about? First of all, as I said, even the reactive power flow is not defined as a parameter, sole parameter in the standards. Since the voltage regulation is a direct effect of reactive power flow, and losses also are a direct effect of reactive power flow, I would like to get the reactive power flow as one of the main problems. And which cause reactive power flow in the power system? All type of loads which have inductance and capacitance components are generating or requiring reactive power. For example, a motor needs reactive power in order or to get, generate that rotating magnetic field, and of course generating that torque to generate that active power output. So for transformers, again, in order to transfer power from one winding to another winding, we need to create a magnetic field, and for that magnetic field we need inductive reactive power. On the other hand, medium voltage cables in our system, since medium voltage cables are acting as a capacitors, because of there is a conductor, there is an insulation material, and also there is another conductor, which is the ground itself, earth. So we have two conductor devices and one insulation material between these. So the medium voltage cables are acting as capacitors, and they are generating capacitors, capacitor reactive power. So all these reactive power flow results in our system more losses, less capacity utilization, and also voltage problems. I mean, if the capacitive reactive power flow is high, then the voltage rise problems appear. On the other hand, if the inductive reactive power flow is high, we observe low voltage problems. So these are the causes and the effects of the reactive power: under voltage, over voltage, voltage fluctuations, the unbalance. Of course, there's an unbalance if the reactive power is also unbalanced, and the resonance and the harmonics are also some effects of these reactive power problems, because at the end of the day, in order to avoid the reactive power flow, we mostly use cap banks, and these cap banks generate, on the other hand, harmonic problems if there are harmonics on the power system. And in order to avoid reactive power flow, we use cap banks, we use passive harmonic filters, we use FET devices like SVCs, MCRs, STATCOMs, or active power filters. As I said, the reactive power flow is one of the important parameters in the system with harmonics. You know, the harmonics, we ideally we have the voltage and the current on this electrical system as a sinusoidal, pure sinusoidal with 50 or 60 hertz frequency, and there is no any delay or any angle between the voltage and current. This is the ideal case. On the other hand, such loads like the motor drives, symmetrical power supply, electronic ballast, arc furnaces, induction furnaces, welding machines, cranes, all these equipment generate harmonics because they are using, semiconductor devices, and these semiconductor devices have some, the switching, and because of these switchings, the current waveform becomes disturbed, and these, we remember, the Fourier transformation. You remember the Fourier fast transformation, so we can express any periodical signal, distorted signal, actually with the harmonics, with its harmonics. So we have 50 hertz, and we have, for example, 150 hertz, and the 250 hertz. So all this become, and you see for example, the waveform on this slide. You see there's a distorted waveform, and if we have an FFT on this waveform, we have these fundamental and harmonics. So we need to avoid harmonics because it creates additional losses. It creates additional stress on equipments, and also it can generate or it can trigger resonance problems in the power system. You know the resonance issue actually. If yes, let's say if there is a system and then it has a resonance frequency, for example, 250 hertz. If you inject 250 hertz current into the system, if it is parallel resonance frequency is 250 hertz, then even very, very small current being injected to this system creates bigger and bigger currents and the voltage on the system. In many systems, there are resonance problems, not only electrical system. On mechanical systems, also there are resonance problems. You may know that, for example, in San Francisco bridge, sometimes actually because of the the resonance frequency and the wind and the cars or the vehicles passing the bridge can create this resonance, and also the bridge can be oscillating like this here. So the resonance problem is very important because if the system's parameters are, I mean if the damping in the system, I mean the losses on the system, if not so much, this resonance problem can create bigger and high actually voltage and the current problems on the system. And the solution for the resonance is, we use mostly the passive filters, and we use active filters, series reactors, or unified power quality conditioners in order to, first of all, in order to eliminate harmonics. If we eliminate harmonics, we eliminate the resonance risk. Or we put some additional equipment into the system, and we can change the frequency of the resonance. So, for example, if the resonance of the system, parallel resonance frequency of the system is 250 hertz, we can put some additional reactors, then we can actually shift this parallel resonance frequency up to, for example, 180 hertz. So if even we inject a fifth harmonics into the system, since the resonance frequency shifted, there will be no risk. So it is, of course, we need to study and we need to find what is the parallel resonance frequency of the system and how we can solve it. And the passive filters are the most common solution for eliminating the harmonics, because it's formed from the combinations of passive elements like capacitors, inductors, and resistors. And since all these, the passive equipments, it is a low-cost solution. But of course, it is bulky, and since we are using capacitors in this passive harmonic filters, we use passive harmonic filters for two purposes. One is reactive power flow or reactive power compensation, and also eliminating harmonics. And we use reactors and the capacitors together, and we create filters. But these passive filters have limited harmonic filtering performance because it's a passive equipment, and it's a frequency curve. So and if the frequency changes, the filtering performance of the filter, of course, changing. And the pure design can arise severe resonance problems if you don't design the passive filter in a correct way. You might increase the harmonics in the system. Actually, we are putting these passive filters to avoid harmonics or eliminating the harmonics. But if the design is wrong, you can increase the harmonics, and this is very important. So passive harmonic filters require more and detailed system study for proper operation. It is very important. You have to study the system, you have studied the load, and you have put or calculate the parameters of the filters, and you should take some measures if there is a risk of resonance in the system, and you should put the correct design and right thing on the system. And passive filters, you can see on this slide, there are some types of passive filters. First one is on the upper side is high pass filters. We are using these filters mostly for eliminating the higher order frequencies and generally higher than the 13th harmonics. And also the first order low high pass filter, you see the with a resistor and the capacitor in series on the left hand side, first order high pass filter. We use these filters mostly because it is cheap compared to others and the cost effective one. And we use this filter, for example, not only for eliminating harmonics, but also eliminating some transients because of switchings. For example, switching and reactor, or switching and line, or for example, in the system, in order to avoid the traveling waveforms on the high voltage lines, we use also capacitors on the system with the metal oxide varistors. So these are the filters we are using for high frequency applications. You see below the tuned filters. Tuned filters are the common ones. We are mostly using these filters. There are some types, single tuned filters. For example, if we have a load and it creates fifth harmonics, we use a filter having a series resonance frequency of 250 hertz. I mean the frequency of this filter, the inductor and the capacitor, they perform a filter circuit, and the frequency of this filter circuit is 250 hertz. What means? It means that actually the impedance of the filter at that specific frequency is ideally zero. So if you inject a current 250 hertz from the load side, since this impedance is ideally zero, then this current does not flow to the grid, but it flows through the filter circuit. This is the main idea of the filters. So the series resonance frequency of the filter is the frequency which we would like to eliminate or filter out. There are some other filters, for example, double tuned filter or C-type filter. All these designs are actually used for, of course, the optimum solution. I mean, technical and commercial. The C-type, for example, C-type filters are used very common in arc furnace applications because this low pass filter actually we can eliminate not only the second, third, or fifth harmonics. We can also eliminate the interharmonics generated by the arc furnaces and the high voltage DC transmission systems. As you see in these passive filters, we have only passive elements: inductor, capacitor, and the resistor. So with some different variations with these equipment, we can create filters. But since we are using capacitors in these filters, we are using the passive filters not only for eliminating harmonics, but also for balancing or compensating the reactive power and as a reactive power source. And another reactive power compensation system is the SVCs, static power compensations. This static word actually comes, the static word comes for the semiconductor itself. I mean, actually, it's a dynamic solution. I mean, it is varying very fast. It acts very fast. But since we are using semiconductors, we call this solution as static power compensation. So static denotes for the semiconductor device, not the operation behavior of the system actually. So in the static power compensation system, we have passive filters, fixed passive filters, and we have varying reactive power, which is an inductive reactive power, which is generated by a reactor, but it is controlled by a thyristor valve. You see, and we call it thyristor controlled reactor in the middle, and on the left hand side we have a control system. On the right hand side we have harmonic filter banks, and it acts like this. We have, for example, 10 MVR filter bank, and we have a 10 MVR reactor, but this reactor can be controlled by a thyristor valve, and the reactive power of this inductor can be controlled from 0 to 10 MVR in a continuous way. So the total output of this system becomes from 0 to 10 megawatt capacitive in a continuous way and also in a fast way. Since the thyristor switch can be controlled in 10 milliseconds, we can change the firing angles of the thyristors in 10 milliseconds, so we can change the system reactive power. And you see here another slide. Yes, the operating principle of the thyristor controlled reactor. You see, thyristors are the very old but robust semiconductor devices. We can switch on thyristors whenever we want. So you see the waveforms. If we switch the thyristor at 90 degrees, so the inductor becomes as a pure sinusoidal and the maximum reactive power. But for example, if we fire or send the trigger signal to the thyristor at 150 degrees, so the current becomes like you see in a very low, here but and also not sinusoidal, because there are some regions you see there is no any current. So this is distorted, but the reactive power becomes lower. So thyristor valve is acting here as a valve actually. So we can adjust the reactive power flow from the reactor itself with an electronic system, and we can control the reactive power from 0 to maximum in a continuous way. And the response time of the thyristor is 10 milliseconds. But of course, the total or overall system response time is a couple of 100 milliseconds because we have a controller and PI controller in the system. So the PI controller is working in the feedback. We have a closed loop control. There is a closed loop control, and we have a PI control on that. So the total response time of the system is couple of 100 milliseconds, actually around 5 to 6 cycles in a typical way. And what are the main features of the SVCs? Static var compensators. First of all, reactive power compensation. And the second one is the reducing flicker. The flicker actually generated mostly by very fast and varying loads like induction furnaces or arc furnaces. So this SVC can work very fast and also can generate unbalanced reactive power, so it can reduce flicker. And flicker, is the changing. It can be observed mostly on old-fashioned lamps, not the new ones. That there is a flickering on the lamp light. It is actually not an electrical thing, but it is important because it is an 8.8 hertz oscillation actually, and so according to the literature actually, this 8.8 hertz oscillation can trigger some attacks on the people having epilepsy. So that is important for health as well. But of course nowadays we are using new types of lightings in our houses, and the most efficient ones. So these things don't create flicker anymore, and it can eliminate harmonics and it can eliminate the unbalance issues. And the benefits of the SVCs. SVCs are mostly used with big loads. I mean the mining industry, cement industry, iron and steel industry, all these industries, because the SVCs are big systems, and it can be used with these type of loads, and there's a reduction in active energy losses because of improving reactive power flow and filtering the harmonics. So these are the main benefits of the SVCs. And also it balances the system voltage. It is very important because if there is a heavy load having inductive reactive power on this part, and if you don't compensate this inductive reactive power, this heavy load, there will be a voltage drop, and this voltage drop will result in low power transfer from grid to the load. Especially in iron and steel industry, in arc furnaces, it is very important. According to the maximum power transfer theory, the impedance of the load and the impedance of the the system should be matched. So these SVCs are being used to make these impedances matching by eliminating all imbalances and reactive power in the system, and making the voltage very smooth and on the ideal case, and transferring the maximum power from grid to the load. This means that the time to have an melted steel in a shorter time, because if you transfer more power, then you can have the melted the steel in a shorter time. This eliminating the reactive power means that the better utilization of transmission and distribution systems, it's very important, and also increasing the quality of the supply because of eliminating the harmonics. So SVCs are very common in industry, and also in utilities, in grids, also SVCs are being used, especially for large systems. In order to have more stable power grid, we are using SVCs for reactive power support and also voltage support. And these are big systems, like starting from a couple of hundred MVRs. And the magnetic control reactor is another type of SVC. Actually, it's a compact solution, because in this solution, there is a main winding and there is a control winding. And this control winding, actually, this provides a DC superposed magnetization current into the core of the reactor. And so the reactor, actually, the susceptance or the impedance is changing. So the reactive power is also being controlled. So I would like to show here. Yes. Yeah, you see the photo. It's a typical oil-filled reactor, but we have thyristors on top of this reactor, and you see the connections between the control winding and the thyristor. So if we trigger these thyristors on the right time, we can inject like a DC current into the core. So core saturates, and the impedance of the core changing, or impedance of the reactor changing, and of course the output reactive power is changing. So this is a very compact solution. It is very good for voltage regulation, reactive power support, because unlike SVC, actually, the conventional thyristor controlled reactor, this solution is very compact and needs low footprint, and also not so much complicated control system. And important thing is that there is no need any for cooling system. In conventional SVCs, you need a very big and powerful cooling system. But here, the MCR, you don't need any cooling system. The control system is very simple, and it is very compact. And also it can be connected directly to medium voltage or high voltage. You see, because this control winding is on the same core with the main winding. So, for example, this photo is from a 36 kV system, but you can connect these MCR up to the couple of 100 kilovolts as well. There is no issue about that, and it has a lower cost, of course, lower harmonic distortion, easier maintenance. So, what is the main disadvantage then? We are talking only advantage. The main disadvantage here is that the response time is a bit long compared to SVC. So the MCR cannot be used for flicker reduction, because for a flicker reduction, we need very fast response. So this MCR cannot be used flicker response, flicker correction, or flicker elimination, and also cannot be used very, very fast varying loads like arc furnaces. But still, the response time is around 1 second. So any load having 1 second variation in reactive power, these MCRs can be used as a very low cost and optimum solution. And we are using a lot in our country. And yet we have STATCOMs, static compensators, synchronous compensator. This name comes from the synchronous compensator. You might know that we are using synchronous generators for generating reactive power. And the static synchronous compensator means that still we are using the same idea, but it is static. I mean, again, we have semiconductor devices. Like STATCOM is like an UPS in our offices, in our houses. We are using uninterruptible power supplies. Actually, STATCOM is working with the same converter topology, actually. But here, STATCOM's main responsibility is generating reactive power, not the active power. A UPS can inject active power, can create active power, but a STATCOM is generating and reactive power. Hence, a STATCOM does not need any power on the DC side. You see on the STATCOM on the left-hand side, we have a capacitor on the DC link of the STATCOM, DC link capacitor. We have a converter, we have a filter circuit, and coupling transformer in order to connect the STATCOM to the medium voltage or the high voltage. So STATCOM is acting like this as a voltage source, and this voltage source is mainly in the same phase with the supply voltage, but the magnitude generated by the STATCOM can be controlled, and they can be lower or higher than the supply voltage. So this, if it is lower, then the capacitive reactive power is coming actually flowing from the grid to the STATCOM, or if the voltage is higher, then the current is injected from STATCOM to the grid. Hence, this current is circulating on the STATCOM itself. Hence, we don't need any additional external power source for STATCOM. STATCOM can operate like here independently. The capacitor on the DC link is being used in order to maintain the DC voltage, because we have a DC, we have a converter, and we are using this DC voltage to create AC on the AC side. But this DC capacitor does not require any additional external source to supply any reactive power. So we don't store any reactive power. The reactive power is just flowing through the grid and the STATCOM itself. We only active power a little amount, that little amount actually for the active power losses of the converter itself. And like SVC, STATCOM also can create reactive power, but since it is a controlled device, unlike the SVC or unlike passive systems, we can generate either inductive or the capacitive from the same converter. It is the main advantage of this STATCOM. And also response time is very, very fast, because in STATCOMs, we are using IGBTs as semiconductor devices, and the response time of the IGBTs are around milliseconds. So the response time is very fast and compared to SVC. Hence, STATCOMs can be used for flicker reduction in power system, especially if you need more flicker reduction ratio. On SVCs, flicker reduction ratio is around 1.7, but with STATCOM you can have up to 2.1, 2.2 flicker reduction ratio with the STATCOMs. So if there is a big flicker problem, you can use STATCOM in order to eliminate these flicker problems, because it can act very fast. But of course, there are some disadvantages of STATCOMs as well. These are the benefits and the advantage or disadvantage, or which one and the when. STATCOM, better dynamic response, reduced installation footprint, and the grid voltage independent performance, and high short time overload capacity. Since the converter is controlled by us as a voltage source, we can inject the current required in a controlled way. And for example, in a STATCOM, you can inject more current for short time periods, because it's up to cooling system, or it is up to temperature rise on the devices. So for a shorter time, for shorter periods, you can inject more power. For example, I will explain in the next slides. We have a system in Australia right now, and we can inject 2 times rated power for 3 seconds with the STATCOM. But for SVC, we cannot, because the reactive power of SVC is limited by the passive equipment and also voltage, because the reactive power is equal to V square over impedance, V square over X. So if the voltage drops, reactive power drops, okay, and if the voltage rises, then the reactive power rises. On SVC, of course, for SVC, by the way, on the STATCOM, since we are using IGBTs, we are using switching frequency, higher switching frequencies. This means that on the STATCOM, switching and the conduction losses are high compared to SVC. And SVC's initial cost is lower, and it needs less maintenance and operational cost. And the SVC's is better for very high power and high voltage applications. The tyrostyle semiconductor is maybe 70 years old semiconductor. So it is very robust for high power applications. So for high power, high voltage, and for bigger systems, SVC can be cost competitive. But for smaller ones, and if you need more fast dynamic response, then STATCOM comes into the picture. And active filters almost same with the STATCOMs. We have the same converter topology, but here the active filter is controlled in a way that generating harmonic currents. So how it works, we have a nonlinear load. It creates an harmonic waveform with fundamental and the harmonic currents. So we measure the harmonics, and we inject the opposite of these harmonics. So we cancel the harmonics on the point of common coupling. So the current on the grid side becomes pure sinusoidal. So mostly the active power filters are low voltage devices, because since we are generating harmonics, the switching frequency of the devices are very high. And since this reason, the active filters are mostly low voltage devices, and they are connected to medium voltage mostly with the coupling or step-up transformers. Where we are using active power filters, mostly in IT industry, in hospitals, in data centers, because since these harmonics, especially the higher order harmonics, can create some problems on the telecommunication devices or the monitoring devices. So we are using active power filters. But active power filter also can work as like a STATCOM. So it can inject it can inject at the same time harmonics and the reactive power together. So active power filter can work as a STATCOM and also can eliminate the reactive power. In low voltage applications, we are mostly using three-phase, 4-wire shunt active filters. The 4-wire means the neutral conductor. So by using the active power filters, we can also eliminate triplen harmonics and the unbalance on the system. So we can eliminate also the neutral conductors, neutral currents on neutral conductors by active filter. It's also a good thing in order to, if we can avoid the neutral currents. Again, the same topology as I told, voltage source converter based circuit topology we have, and the features: current harmonic compensation, voltage harmonic damping, power system resonance, avoiding prevention, power factor correction, and the load balancing are the main features of the active power filters. And the good thing, since the semiconductor devices are becoming cheap daily, so these active power filters and STATCOMs, all this stuff on the low voltage side, especially on the low voltage side, now they become very cost effective devices. We can use active power filters on the low voltage side, maybe rather than using passive filters for eliminating harmonics. And we have some reference projects I would like to explain. For example, this reference project for SVC, it's a 310 MVR project. It is the biggest the steel factory in Turkey, and this SVC is the second biggest industrial SVC in the world. So it's 310 MVR one. It's a very big one. It's being used with an 300 metric tons arc furnace, actually manufacturing steel from scrap. And you see these pictures. We have thyristor valves, we have cooling system, and we have passive harmonic filters. Also generating reactive power and also harmonics. In arc furnace applications, we are using mostly second, third, fourth, fifth, and maybe sometimes so on, harmonic filters in order to eliminate harmonics. And also we have, these are fixed banks. In the system, we have 300 MVR fixed capacitor bank, and also we have 310 MVR variable shunt inductor, which is being controlled by thyristor valves. So we can control the reactive power from 0 to 310 MVR in a continuous way with 10 milliseconds resolution. So it is very important. By the way, in many countries, using SVCs along with the arc furnaces are compulsory. So you must use actually SVC with the arc furnace because of grid codes. But on the other hand, with an SVC in an arc furnace, the production efficiency can be increased more than 10% by SVC, because keeping the voltage on a definite level and eliminating reactive power, eliminating harmonics. So the efficiency can be increased more than 10% with an SVC in an arc furnace application. And the MCR application, we are using mostly as MCRs in distribution systems, in renewable power plants, and also, the regulating the voltage because of the high penetration of hydro and the solar power plants. It is very compact, and for distribution systems, it doesn't require any, complicated or complex maintenance works. So this is very suitable for the grid operators because it doesn't have so much complicated or complex things. We have used more than we have used more than 40 or 50 MCRs in different locations in the country. And this reference project is coming from Australia. This is an STATCOM project, actually in Sydney, Dubbo. It was installed in order to meet the grid codes in Australia with an 100 megawatt solar power plant, because in order to operate the 100 megawatt solar power plant, there should be a reactive power support and also voltage right through capability. And we provided this capability with using STATCOM. Actually, it is an 8 MVR STATCOM connected to 10.5 kV bus using coupling transformers. We have four containers. It's a containerized solution. In each container, we have 2 MVR, and each 2 MVR actually is composed of modules of 400 kVR at 480 volts. Actually, the rated voltage of the converter is 690 volts, but the operating voltage is 480 volts. So each module is 400 kVR and 480 volts, and it becomes 8 megawatt on the medium voltage side. And as I told previously, in the STATCOM, for example, we can inject 16 megawatt 2 times rated power for 3 seconds. So if there is a fault in the power system, maybe short circuit or maybe a heavy load switching, so the voltage is rising or voltage is oscillating, this STATCOM can inject more power to support the grid in terms of voltage. So this system is in Australia and been operating for the 1.5 years. Now, actually, I finished my presentation, and I'm sorry, my good author is here, and I finished my presentation, and I would like to get the questions. I will be glad to answer them.
Thank you very much, Alper. Yeah, it's been great. We have received one question here. We've gone to the presentation to Q&A mode. Great. Yeah, we've got a question from Yuns Armand. He said, can you please clarify the impedance matching mentioned in SVC used for arc?
Yep, sure. Actually, as you know, in order to have the maximum power transfer, we should have a matching between the system impedance and the arc furnace impedance. And the arc furnace deep measurement, deep resistance values in the literature, we call it deep resistance value. So if the arc furnace is working purely resistive, then there will be a matching between the system and the transformer. However, if, for example, three-phase, in an arc furnace, we have 3 electrodes, actually, which are injected into the scrap and creating an arc there, and also this arc power actually melting the steel. But sometimes actually, there is no 3 electrodes in the scrap, but sometimes there are 2, sometimes 1 electrode is broken or scrap is actually not there. So there is an always unbalanced impedance there on the electrode side, and also the nature of the arc is also inductive. So we are creating an impedance there, which is eliminating this inductive part as well. In the literature, maybe you can search on the web the Steinmetz equations, actually. Steinmetz. I type there. Yeah. On the chat box, you can see the Steinmetz equations. So, and actually in the SVC control theory, we are using the Steinmetz equations, and we can balance total unbalanced load as a 3-phase load, balanced load. So then there will be from the grid, if you see the load as a 3-phase balanced resistive load. So you don't see any unbalance, you don't see any reactive power or reactive impedance there. You see only balanced and resistive impedance from the grid side. So this SVC is being used for this purpose in order to matching the impedances and also assuring the maximum power transfer from grid to the arc furnaces. Okay, I hope this explanation is sufficient.
We've got another question from Nabil. He's asking if we can share the presentation. You can actually access the presentation on the event board at the top right-hand corner of the screen. You see event board there, and if you click on that one, you will see event info and shared files. And underneath shared files, the presentation is the one called Endoks Power Quality eng.pdf. And you can also find the brochures there as well for the products.
Okay.
I guess, yeah. seems like that's all the questions we have. We have got a very short survey, which is very important for us. If you can complete the survey quickly, yes, stepping stone for the following webinars that we are planning on holding. And I think that's it. Thank you very much, Alper. It's been a great presentation. It's great to have you always online.
Yeah, actually, welcome, Serdar. It was a pleasure for me. I hope soon we will again meet together in person in Australia.
Yes, look forward to that.
Yes,
Definitely.
yes. And thank you for all thanks to all attendees, of course, for watching this webinar. And if you have any question, you can reach to me either from LinkedIn, or I am now typing my email address as well, or you can reach out Serdar, of course. Don't hesitate if you have any question. And David, you're welcome, David. It's been a long time. Yeah, our friends here. Thank you.
Yeah, some of the long, unheard, unseen faces are here, which is great.
Yeah. Okay, and thank you, and see you all then.
Thanks very much. Yeah, look forward to having you on another one. We are planning on continuing this series with going into more detail in specific areas, and hopefully you have identified that in the survey as well. Yes, looking forward to meeting yet another one. Thank you very much. Have a fantastic day.
Thank you. Bye.